What if I told you the first galaxies in our universe didn't look anything like the glittering spirals and glowing orbs we see today? Picture this, a cosmos so young, so raw, that the very fabric of space was still stitching itself together, and the first flickers of starlight were only just piercing the darkness. These primordial galaxies weren't just the ancestors of our Milky Way, they were cosmic pioneers, blazing trails through an infant universe we're only beginning to understand. And here's the wildest part. Scientists have uncovered not one, not two, but 30 mind-bending theories about how these ancient giants came to be. Some suggest they formed in violent collisions of gas and dark matter, while others propose they were sparked by the screams of the universe's first black holes. Think about that for a second. Every galaxy we see today, every swirling arm, every glittering cluster traces its lineage back to these mysterious, chaotic beginnings. But how did they take shape in a universe that was still figuring itself out? What forces sculpted them, and why do some of these theories sound more like science fiction than astrophysics? That's the journey we're about to take together, a voyage back over 13 billion years, to a time when the cosmos was a blank canvas and the first strokes of galactic light were just starting to appear. You might wonder why this even matters. Well, these galaxies aren't just relics of the past, they're the key to understanding everything. They set the stage for stars, planets, and eventually us. Without them, the universe would still be a silent, empty void. So buckle up, because we're diving into the most thrilling frontier of modern astronomy. 30 theories about the universe's first galaxies, each one more astonishing than the last. By the time we're done, you'll see the night sky and our place in it in a whole new light. One of the most radical theories about the birth of the first galaxies flips the script entirely. What if galaxies didn't form around stars, but instead grew from the ravenous hearts of ancient black holes? Picture the early universe, a seething ocean of gas and dark matter, still reeling from the Big Bang. In this chaos, some scientists believe monstrous black holes, far heavier than any we see today, sprang into existence first, lurking in the void like gravitational traps. These weren't the quiet, well-behaved black holes of modern galaxies. These were primordial beasts born from the collapse of dense patches of spacetime itself, and they may have served as the seeds for everything that came after. Here's how it could have worked. As these black holes devoured the surrounding gas, they unleashed torrents of energy, heating up the cosmos and carving out vast bubbles in the primordial soup. But their gravity was so immense, it acted like a cosmic magnet, pulling in gas and dark matter until entire galaxies began to whirl around them. Recent supercomputer simulations show something astonishing. When you drop a supermassive black hole into a virtual early universe, it doesn't just sit there. It triggers a frenzy of star formation, sculpting swirling disks and glittering clusters in its wake. Now, here's where it gets even stranger. Some of these primordial black holes might not have formed from dying stars at all. They could be relics of the Big Bang itself, lurking in the shadows of spacetime since the very beginning. If that's true, then the first galaxies weren't just built by black holes, they were built for them. It's a cosmic chicken and egg question that rewrites the story of how structure emerged in our universe. And if we ever spot one of these ancient monsters hiding in the distant cosmos, it could be the missing piece to understanding why galaxies look the way they do. But this theory isn't without its skeptics. If black holes came first, why don't we see more galaxies with them at their centers today? And how could something so destructive also be the architect of creation? That's the beautiful contradiction at the heart of this idea. Sometimes, the universe builds by first tearing itself apart. But what if black holes weren't the only architects of the early universe? Imagine an invisible hand shaping the cosmos long before stars or black holes even existed, a ghostly scaffold woven from the fabric of dark matter. This shadowy substance, which outnumbers ordinary matter 5 to 1, might have been the universe's first cosmic engineer quietly pulling strings behind the scenes. Here's the fascinating twist. While dark matter doesn't interact with light or normal matter the way atoms do, its gravity is relentless. In the early universe, tiny ripples in the dark matter, leftover tremors from the Big Bang, began collapsing under their own weight. Like dust gathering in the corners of an untouched room, these invisible clumps grew denser and denser, forming vast, tangled structures scientists now call the cosmic web. Picture a spider's silk spun across billions of light years, with dark matter as the threads and galaxies as the dewdrops caught in its strands. This cosmic scaffolding didn't just sit there, it became a gravitational trap for ordinary gas. Hydrogen and helium, the universe's raw materials, slid down these invisible slopes, pooling in the deepest wells of dark matter's grip. Only then, in these dense pockets of gas, could the first stars ignite, lighting up the darkness like fireflies in a cavern. Supercomputer simulations show something remarkable. Without dark matter's pull, ordinary matter would have spread too thin, delaying galaxy formation by billions of years. The cosmic web didn't just influence where galaxies formed, it dictated how they formed, shaping their sizes, speeds, and even their fates. Yet mysteries linger. Why do some galaxies seem to lack the expected dark matter halos? Could there have been exotic types of dark matter behaving differently in the early universe? The answers might lie in the faintest, most distant galaxies we're only now beginning to detect whispers from a time when darkness ruled the cosmos. One thing's certain, dark matter didn't just build the universe's first galaxies. It built the blueprint for everything we see today. Before there were galaxies as we know them, before planets or even the elements that make up our world, the universe hosted a breed of stars so strange and powerful they defy imagination. These were the population 3 stars, cosmic giants born from nothing but the pristine hydrogen and helium left over from the Big Bang. Without a single speck of carbon, oxygen, or iron to weigh them down, they burned brighter, hotter, and faster than anything that exists today. Some may have been hundreds of times more massive than our Sun, shining with the intensity of millions of modern stars, and their deaths may have been the very spark that ignited the first galaxies. Think of the early universe as a vast, unlit forge. Population 3 stars were its first anvils, hammering raw hydrogen into heavier elements through nuclear fusion. But unlike today's stars, which fade gradually, these behemoths lived fast and died violently. When their cores ran out of fuel, they didn't just collapse, they detonated in cataclysmic supernovas so energetic they could outshine entire galaxies. These explosions weren't just spectacular light shows. They were cosmic alchemy labs, forging the first heavy elements and blasting them into space like seeds scattered by a celestial wildfire. And here's where the story gets even more fascinating. Those scattered elements, carbon, silicon, iron, became the building blocks for everything that followed. The second generation of stars, smaller and longer lived, formed from this enriched gas. Planets coalesced from the debris. And crucially, these heavier elements allowed gas to cool faster, collapsing into denser clouds that could birth stars in greater numbers. In other words, the deaths of population 3 stars may have been the turning point that transformed the universe from a realm of isolated giants into one teeming with galaxies. Yet for all their importance, we've never actually seen one. These stars burned out billions of years ago, and their light is so faint and distant that even our most powerful telescopes struggle to catch a glimpse. But astronomers aren't giving up. They're scouring the farthest edges of the observable universe, looking for the chemical fingerprints these stars left behind, patches of gas with no heavy elements, or the faint afterglow of their supernova. If we ever find one, it would be like uncovering the fossil of a cosmic titan, a relic from the universe's fiery childhood. There's a haunting beauty to this idea. The very stars that vanished without a trace may have built the foundations for everything we know. Without their explosive deaths, galaxies might never have grown beyond faint smudges of light. So the next time you look up at the night sky, remember, you're not just seeing stars, you're seeing the legacy of giants. Now here's a theory that sounds like the universe hit fast forward. What if some of the first galaxies didn't form star by star, but erupted into existence all at once? Imagine a primordial gas cloud so massive, so dense, that gravity didn't just nudge it into forming stars, it crushed the entire thing into a galaxy in one staggering collapse. These hypothetical direct collapse galaxies would have been cosmic shortcuts, bypassing the slow simmer of starlight to become fully fledged galaxies almost overnight. The math behind this is staggering. In the early universe, vast reservoirs of pure hydrogen and helium gas untouched by heavier elements could have reached critical mass. Without dust or metals to help them cool and fragment, these clouds wouldn't break into stars like modern nebulae. Instead, their sheer weight would trigger a runaway collapse with the entire cloud plunging inward at once. The result, a monstrous baby galaxy, hundreds of times heavier than our Milky Way, glowing with the heat of its own violent birth. At its heart, the pressure would be so extreme it might spawn a supermassive black hole in a single bound, a gravitational titan born not from a dying star but from the wreckage of an entire galactic womb. But here's where things get contentious. If these galaxies existed, why haven't we seen them? Telescopes like the James Webb are peering deeper into the past than ever, yet the evidence remains elusive. Some astronomers argue we're looking for ghosts, that the conditions needed for direct collapse were rarer than the theory suggests. Others counter that we simply haven't found them yet. After all, these galaxies would have been bizarre creatures, vast, dim, and bloated with gas, lacking the glittering star clusters we associate with modern galaxies. They might hide in plain sight, masquerading as faint smudges at the edge of our observations. There's another twist. If direct collapse galaxies did exist, their black holes could solve a mystery that's puzzled scientists for decades: how supermassive black holes grew so enormous so quickly. A handful of these collapses could have seeded the universe with ready-made monsters, explaining why we find billion solar mass black holes in galaxies barely a billion years old. It's as if the universe cheated, building its heaviest objects first and working backward. Yet skeptics point to the delicate balance required. The gas clouds couldn't be too hot or too cold, too large or too small. Even a whisper of turbulence or a trace of heavy elements might scatter the gas into stars instead. That's why some researchers call direct collapse galaxies the unicorns of cosmology, possible in theory, but vanishingly rare in practice. But in a universe as vast as ours, even the rarest events might leave echoes. And if we ever catch one in the act, it would rewrite our understanding of how galaxies are born. After all, in the chaos of the early cosmos, sometimes the rules weren't just broken, they were never written at all. Picture the universe not as a vast emptiness dotted with galaxies, but as a living, breathing network, an intricate tapestry of glowing threads where matter flows like rivers in the dark. This is the cosmic web, the grand architecture of the universe, and some scientists believe it wasn't just the backdrop for galaxy formation, it was the fuel. Hidden within these filaments, colder than the void between them, rivers of pristine gas may have funneled into the earliest galaxies, igniting starbirth with a ferocity we can barely comprehend. Here's how it could have happened. In the early universe, dark matter's gravity sculpted the cosmic web into a labyrinth of slender filaments, meeting at dense knots where galaxies would later bloom. But between these knots, something extraordinary was occurring. While most of the universe was a searing plasma too hot to form stars, narrow streams of gas shielded by darkness somehow stayed frigid. These weren't just tendrils of hydrogen, they were cosmic ice highways barely warmer than absolute zero, sneaking through the heat unscathed. And when they reached the intersections of the web, they crashed together in silent, invisible deluges. The result, a spark in the dark, As these icy rivers collided at the web's nodes, their sudden density triggered violent starbursts, galaxies igniting like matches struck against the fabric of space-time. Computer simulations reveal something mesmerizing. These filament-fed galaxies wouldn't grow slowly, nibbling on nearby gas. They'd feast, gulping down entire rivers of cold fuel in bursts of frenzied star formation. Imagine a fire spreading not ember by ember, but along soaked trails of gasoline. That's how quickly the first galaxies could have lit up the cosmos. But there's a catch. For this to work, the gas had to stay cold enough to flow smoothly, a puzzle that stumped researchers for years. Turbulence, cosmic radiation, even the faint glow of the first stars should have heated it into useless plasma. The answer might lie in an unexpected ally, dark matter again. Some theories suggest its gravity acted like a cosmic insulator, shielding the gas streams from outside heat while herding them toward the filament's intersections. It's as if the universe built hidden pipelines to deliver its star-making fuel. Now, here's the twist. These filament-fed galaxies wouldn't look like the neat spirals we know today. They'd be misshapen, chaotic, their stars born in fits and starts as gas gushed in from multiple directions. Some might have even been strung along the filaments like beads on a necklace, forming the universe's first galactic chains. And if we could peer back far enough, we might catch their last echoes, faint, bluish galaxies clustered along the ghostly ribs of the cosmic web, their light stretched by 13 billion years of cosmic expansion. The hunt for proof is already underway. Telescopes like the James Webb are scanning the deepest voids, not for isolated galaxies, but for patterns, alignments of ancient starlight that trace the bones of the cosmic web. And if they succeed, it would mean galaxies didn't just form within the web, they were born from it, sculpted by rivers of cold gas we're only now learning to see. It's a reminder that even in the vastness of space, everything is connected, and the darkest threads might be what lit up the universe. What if galaxies didn't start as mighty cosmic titans, but as tiny, invisible seeds so small you could hold 1,000 in the span of a single star? This theory rewinds the story of galaxy formation back to its humblest beginnings, suggesting the universe built its grandest structures piece by piece, like a cosmic jigsaw puzzle. Mini halos, clumps of dark matter no heavier than a star cluster, may have been the unsung heroes of the early cosmos, merging over and over until they snowballed into the galaxies we know today. Picture the early universe not as a blank slate, but as a swirling sea of minuscule dark matter halos, each one a gravitational whisper compared to the giants we see now. These halos, some barely wider than our solar system, would have been far too small to ignite stars on their own, but as they collided and tangled, their combined gravity grew stronger, pulling in more gas, more dark matter, and more halos. Like raindrops merging into puddles, then streams, then rivers, these mergers could have built galaxies from the ground up, one tiny step at a time. The beauty of this theory lies in its patience. Unlike the explosive births of direct collapse galaxies or the fiery chaos of population 3 stars, mini halo mergers suggest a slower, more methodical universe. Supercomputer simulations show something mesmerizing. When you let these tiny halos dance under the laws of gravity, given enough time, they do clump together into galaxy-sized structures. And because dark matter doesn't collide or heat up like normal gas, these mergers wouldn't have triggered violent starbursts, just a steady, silent accumulation of mass. But here's the twist. While this process seems elegant, it has a glaring problem: time. The universe was only a few 100 million years old when the first galaxies flickered to life. Could enough mini halos have merged in that brief window to build something as vast as the Milky Way? Some researchers argue yes, that the early universe was so dense with these tiny halos, mergers happened at a breakneck pace. Others counter that we're missing a piece of the puzzle, like an unseen force that accelerated the process. There's another fascinating layer. If mini halos were the building blocks of galaxies, their remnants might still be hiding in plain sight. Dwarf galaxies, small, faint companions to giants like Andromeda, could be the last survivors of this ancient merging frenzy. Some even appear to orbit within vast clouds of dark matter, like echoes of the halos they once were. Yet skeptics point to the universe's largest galaxies, which seem too big, too soon for this gradual process. Could mergers alone explain behemoths that existed when the cosmos was barely a toddler? That's where the theory stretches its legs, proposing that mini halos didn't just merge randomly. They followed the hidden highways of the cosmic web, funneled into collisions by the universe's own scaffolding. The debate isn't just academic. If mini halos were the true architects, it means galaxies weren't born in isolation. They're the product of countless invisible handshakes across cosmic time, a reminder that even the grandest structures can grow from the smallest beginnings. And somewhere out there, in the depths of space, other halos might still be merging quietly, building the galaxies of tomorrow. Now imagine a cosmic beacon so powerful, its light could outshine entire galaxies, a quasar. These brilliant monsters, powered by supermassive black holes feasting on gas at the centers of young galaxies, weren't just cosmic oddities. They might have been the universe's first midwives, using their searing radiation to sculpt the very galaxies that birthed them. At first glance, this seems backward. How could something so destructive also create? Picture a quasar in the early universe, its jet of energy screaming across space like a blowtorch. That radiation should tear gas clouds apart, scattering star-forming material to the winds. But here's the paradox: under the right conditions, quasars don't just destroy. They compress. As their radiation slams into surrounding gas, it doesn't always push it away. Instead, it can crush gas into dense, cooling shells like snow piling up in front of a plow. These pressurized regions then collapse under their own weight, igniting firestorms of star formation at rates hundreds of times faster than we see today. The numbers are staggering. Some simulations show quasars triggering star formation so intense, entire proto-galaxies could assemble in just tens of millions of years, a blink in cosmic time. And the evidence might be hiding in plain sight. Modern telescopes have spotted distant galaxies with bizarre properties, huge, compact, and glowing with the light of countless newborn stars. Their chemistry matches what you'd expect if a quasar's radiation had supercharged their growth, leaving behind clusters of stars so tightly packed they'd outshine our entire Milky Way in a space no larger than our solar system. But there's another twist. Quasars didn't just pressurize gas, they may have enriched it too. As these black holes devoured matter, they spit out torrents of heavy elements forged in their accretion disks, seeding the surrounding gas with the ingredients for rocky planets and life. In this scenario, the first galaxies weren't just born from chaos, they were forged in the crucible of a quasar's fury, their stars and planets built from the ashes of a black hole's feast. Yet mysteries remain. Why do some quasars seem to trigger star formation while others sterilize their surroundings? Could it depend on the angle of their jets or the density of nearby gas? The answers might lie in the upcoming generation of telescopes, capable of spotting these cosmic fireworks at the exact moment they ignite a galaxy. One thing's certain: if quasars really did midwife the first galaxies, it adds a delicious irony to the story of our universe. The darkest objects in existence might have been the very ones that brought light to the cosmos. The early universe wasn't just a calm sea of gas. It was a roaring storm, a churning cauldron of turbulence so violent it could have been the secret ingredient in galaxy formation. Picture a primordial gas cloud not as a smooth, floating mist, but as a hurricane with winds screaming at thousands of kilometers per second, twisting and tearing at itself. This chaos, far from slowing things down, might have been the universe's shortcut to building galaxies at breakneck speed. Here's why turbulence changes everything. In modern nebulae, gas tends to collapse slowly, cooling and settling into star-forming pockets over millions of years. But in the early universe, things were different. Without heavy elements to help radiation escape, heat built up like steam in a pressure cooker, making gas resistant to collapse. Turbulence solved this by doing something counterintuitive. It didn't just stir the pot, it created dense knots in the chaos. Think of it like whipping cream. The faster you stir, the more clumps form. Those knots, squeezed by the surrounding turbulence, reached critical density faster than calm gas ever could, igniting stars in a fraction of the time. Computer simulations reveal something astonishing. When researchers plug in turbulent gas clouds from the early cosmos, galaxies don't just form, they explode into existence. Shockwaves ripple through the gas, carving it into intricate filaments and clumps that collapse almost instantly. Some of these turbulent nurseries could have birthed entire generations of stars in one frenzied burst, skipping the gradual buildup we see today. It's as if the universe discovered a cheat code. When gravity isn't enough, chaos picks up the slack. But there's a twist. Turbulence doesn't just accelerate formation, it leaves fingerprints. Galaxies born from this chaos wouldn't have the orderly spiral arms or smooth halos we're used to. Instead, they'd be lumpy, asymmetrical, with stars scattered in odd clusters like splatters from a cosmic paintbrush. Some astronomers argue we've already spotted these oddballs in deep-field images, ancient galaxies that look more like shrapnel from an explosion than the majestic islands of light we know. The real mystery, where the turbulence came from. Some theories point to the aftershocks of the Big Bang itself, ripples in space-time that never fully smoothed out. Others suggest it was the work of the first supernova, their explosions slamming into nearby gas like cosmic tsunamis. There's even a wild idea that dark matter, swirling in ways we don't yet understand, could have stirred the pot invisibly from the shadows. One thing's certain, if turbulence really did supercharge galaxy formation, it means the universe's first structures weren't built on patience. They were forged in the frenzy of a storm we're only just beginning to comprehend. And somewhere out there, in the echoes of those ancient whirlwinds, the recipe for a galaxy might still be written in the chaos. Hidden beneath the chaos of the early universe, invisible threads may have pulled the strings of galaxy formation, primordial magnetic fields. These weren't the weak, scattered fields we see today. They were cosmic force fields woven into the fabric of space itself, strong enough to sculpt gas into galaxies with a precision gravity alone could never achieve. While dark matter built the scaffolding, magnetic fields might have been the universe's unseen choreographers, guiding the spin, shape, and even the destiny of the first galaxies. Picture the early cosmos as a vast, magnetized sea. As the first clouds of hydrogen and helium collapsed under gravity, these magnetic fields didn't just sit idle. They twisted and braided the gas like invisible fingers molding clay. Here's the stunning part. Simulations show that when you add primordial magnetism to the mix, gas doesn't just fall inward haphazardly. It spirals, forming disks with a mathematical elegance that mirrors the graceful arms of modern spiral galaxies. Without magnetic fields, gas clouds tend to crumple into messy blobs, but with them, the chaos organizes itself, as if the universe had a hidden blueprint for beauty. But how did these fields form in the first place? One theory suggests they were born in the fires of the Big Bang itself, when space-time was so energetic that quantum fluctuations could have stretched into cosmic-scale magnetic threads. Another idea points to the violent deaths of the first stars, supernovas so powerful their shockwaves magnetized entire regions of space, leaving behind faint but persistent fields. Whatever their origin, their influence was profound. By subtly resisting the random motion of charged particles, these fields acted like cosmic traffic cops, directing gas flows into coherent structures rather than letting it scatter like smoke in the wind. The evidence is mounting. Astronomers have detected faint magnetic fields in some of the universe's oldest galaxies, fields far too strong and organized to have formed later in cosmic history. Even more tantalizing, galaxies with well-defined spins and disk shapes appear more frequently in regions where simulations predict primordial magnetism was strongest. It's as if the universe's first magnetic imprints left a lasting signature, a ghostly hand guiding galaxies toward order amid the chaos, yet mysteries remain. Why do some galaxies seem to ignore this magnetic influence, forming irregular shapes despite the fields around them? Could magnetic fields have also hindered galaxy formation in some regions, locking gas in place instead of letting it collapse? The answers might lie in the subtle interplay between magnetism and turbulence, a dance of forces we're only beginning to understand. One thing's certain: if primordial magnetic fields really did shape the first galaxies, it means the cosmos wasn't just built by gravity and darkness. It was sculpted by forces unseen, written in a language of invisible lines we're just now learning to read. To understand how the universe's first galaxies might have been shaped by events almost too ancient to comprehend, we need to rewind time further back than stars, further back than atoms, all the way to the first trillionth of a second after the Big Bang. This was the era of cosmic inflation, a blink so brief it defies human intuition, yet so powerful it imprinted the entire cosmos with a hidden pattern. And here's the mind-bending part: those primordial quantum ripples frozen into spacetime during inflation could be the very reason galaxies cluster the way they do today. Think of the infant universe as a blank canvas stretched thinner than anything we can imagine. During inflation, spacetime expanded faster than light itself, magnifying tiny quantum fluctuations, random wrinkles in the fabric of reality, into cosmic-scale undulations. These weren't just microscopic quirks, they were the seeds of all future structure. As inflation ended, those amplified ripples became slight density differences in matter and energy, like invisible fingerprints pressed into the hot plasma of the early universe. Over billions of years, gravity sculpted those dense patches into galaxies, while the emptier regions stretched into vast cosmic voids. The evidence is etched across the sky. When astronomers map thousands of galaxies, they don't see a random scatter, they find a frothy, web-like structure with galaxies strung along filaments and clustered at intersections. This isn't just chaos, it's a reflection of those primordial quantum patterns stretched to cosmic proportions. Even more astonishing, the statistical distribution of galaxies today matches predictions made from quantum physics equations describing inflation. It's as if the universe left us a mathematical love letter from its first moments, written in the language of galaxies. But how exactly did quantum jitters become galactic cities? The secret lies in gravity's patience. Those early density variations, though minuscule, just 1 part in 100,000, were enough to tip the scales. Slightly denser regions pulled in more matter over eons, growing into galaxy clusters, while underdense zones emptied out. Supercomputer simulations show this process with eerie precision. When you input inflationary quantum fluctuations into virtual universes and hit play, they evolve into structures indistinguishable from our own cosmic web. Yet mysteries linger. Why do some galaxy clusters seem slightly more tightly packed than inflation predicts? Could there have been exotic physics during inflation that tweaked the quantum noise? Some theorists speculate about multiple inflationary fields or even collisions between bubble universes events that might have left their own fingerprints on galaxy distribution. Others suggest dark matter's odd behavior could have reshaped those primordial patterns in ways we're only beginning to grasp. The hunt for answers isn't just about the past. If we can decode inflation's imprint on galaxies, we might finally understand what triggered the Big Bang itself. Every galaxy, then, isn't just an island of stars. It's a fossil from the universe's quantum infancy, whispering secrets about the moment everything began. Long before galaxies took shape, the universe was a sea of seething plasma, a superheated soup of particles so dense that light couldn't travel more than a hair's breadth before being absorbed and re-emitted. But within this chaotic inferno, something unexpected was happening: sound waves. Not the gentle ripples we know today, but colossal pressure waves booming across the cosmos like the heartbeat of creation itself. These weren't just random noises, they were baryon acoustic oscillations, and their echoes might have dictated where galaxies would form billions of years later. Here's how it worked. In the first few 100,000 years after the Big Bang, the universe was so hot that protons and electrons couldn't combine to form atoms. Instead, they existed as a plasma with photons, particles of light, bouncing endlessly between them. But this plasma wasn't uniform. Tiny quantum fluctuations from inflation had left some regions slightly denser than others, and gravity began pulling matter toward these overdensities. As matter rushed inward, however, the photons trapped in the plasma pushed back, creating a tug of war between gravity and radiation pressure. The result: spherical sound waves expanding outward at nearly 2/3 the speed of light, compressing matter at their edges like cosmic tsunamis freezing mid-crash. When the universe finally cooled enough for atoms to form, an event we call recombination, those frozen waves left an indelible mark. The peaks of these oscillations became slightly denser patches of matter, while the troughs remained emptier. Over time, gravity amplified these differences, with galaxies forming preferentially where the waves had piled matter up. But here's the twist: because these sound waves had a very specific wavelength, about 500,000 light-years across, they imprinted a scale on the cosmos. Today, when astronomers map millions of galaxies, they find a curious pattern. Galaxies are slightly more likely to be separated by this exact distance, as if the universe were whispering its ancient rhythm through the arrangement of stars. Supercomputer simulations bring this eerie prediction to life. When researchers input these primordial sound waves into virtual universes, the resulting galaxy distributions match our observations with uncanny precision. It's as if the universe left us a fossil record not in rock, but in the very spacing of galaxies, a cosmic fingerprint from when time itself was young. Even more astonishing, this pattern isn't just a relic. By measuring the precise scale of these galaxy clusters, astronomers can trace how dark energy has stretched the universe over billions of years, turning baryon acoustic oscillations into a ruler for the cosmos itself. Yet mysteries remain. Why do some galaxy clusters seem to deviate slightly from this predicted spacing? Could dark matter's strange properties have altered the wave's propagation, or did something even more exotic, like primordial magnetic fields, twist the pattern in ways we haven't yet imagined? The answers might lie in the next generation of galaxy surveys, which will map the cosmos in greater detail than ever before. One thing's certain: those ancient sound waves didn't just shape the universe's first galaxies. They tuned the cosmos like a grand instrument, and we're only just beginning to hear the music. While cold dark matter has long been the leading theory for how cosmic structures formed, there's a radical alternative lurking in the shadows: warm dark matter. Unlike its heavier, slower-moving cousin, warm dark matter would consist of ultralight particles whizzing through the early universe at speeds just shy of light itself. This tiny difference in mass and velocity wouldn't just tweak galaxy formation, it could rewrite the entire timeline of cosmic dawn. Imagine the early universe not as a canvas for slow, gravitational artistry, but as a flickering dance of particles too nimble to settle down. Cold dark matter clumps easily, pooling into dense halos where galaxies can sprout. But warm dark matter, with its higher speeds, would have resisted clustering at small scales, smoothing out the primordial cosmos like a cosmic iron. The result: a delayed but dramatic transformation. Instead of countless tiny halos merging into galaxies, warm dark matter would have first woven vast, wispy filaments, cosmic highways where gas could flow unimpeded until suddenly gravity's grip tightened and galaxies erupted along these threads all at once. The fingerprints of this process would be unmistakable: In a warm dark matter universe, the first galaxies would appear later than in cold dark matter models, but with a peculiar twist. They'd be fewer in number, yet more evenly spaced, like cities built along an ancient trade route rather than scattered villages. Dwarf galaxies, those faint cosmic afterthoughts, would be especially rare. Warm dark matter's reluctance to form small clumps would have starved them of their building blocks. Even the shapes of galaxies might differ, with warm dark matter favoring smoother, puffier halos over the intricate substructures we see today. But here's where the plot thickens. Some astronomers argue we've already glimpsed hints of warm dark matter in action. Distant galaxies observed by the James Webb Space Telescope appear suspiciously sparse in the universe's adolescence, as if galaxy formation hit a cosmic snooze button. Even more intriguing, certain dwarf galaxies orbit the Milky Way in planes that cold dark matter struggles to explain, but which warm dark matter's streamlined filaments might naturally produce. It's as if the universe left us breadcrumbs and they lead straight to a lighter, faster shadow particle. Of course, the debate is far from settled. Critics point to the staggering success of cold dark matter in explaining large-scale cosmic structures, from galaxy clusters to the cosmic web. Warm dark matter, they argue, would struggle to replicate these without extreme fine-tuning. Others suggest a compromise. What if dark matter isn't purely cold or warm, but a mixture of both? A cosmic cocktail where heavy particles build the scaffolding, while lighter ones sculpt the finer details. One thing's certain: if warm dark matter is real, it would mean the universe's first galaxies weren't just shaped by invisible mass. They were choreographed by the ghostly ballet of particles we're only beginning to understand. And somewhere out there, in the faint glow of those ancient stars, the answer might still be waiting. Among the countless forces shaping the early universe, there's one that often gets overlooked: cosmic rays. These aren't your average particles drifting through space. They're atomic nuclei hurled at nearly the speed of light, carrying enough energy to punch through magnetic fields like bullets through paper. And in the chaos of the young cosmos, they might have been the unsung regulators of galaxy growth, pressing an invisible brake pedal on star formation with every violent collision. Picture the aftermath of the universe's first supernova. When those primordial population 3 stars exploded, they didn't just forge heavy elements. They became cosmic particle accelerators, launching protons and atomic nuclei across space with unimaginable force. These early cosmic rays didn't travel quietly. As they slammed into surrounding gas clouds, they transferred energy like bumper cars in overdrive, heating the gas and preventing it from cooling into stars too quickly. It's a counterintuitive twist. The same explosions that seeded galaxies with life-giving elements might also have kept them from growing too fast too soon. Computer simulations reveal something astonishing. When researchers model galaxy formation with cosmic rays included, the results shift dramatically. Without them, gas collapses rapidly into massive stars, burning out in spectacular supernovae that leave galaxies stunted. But when cosmic rays are added to the mix, they act like a thermostat. Their heating effect creates a more measured pace of star formation, allowing galaxies to grow steadily over billions of years. Some models even suggest this balancing act could explain why we don't see more monstrously large galaxies in the early universe. The cosmic rays were literally holding them back. The evidence for this lies in some of the most distant galaxies we've observed. Many show chemical signatures hinting at periods of intense radiation bombardment, their gas layers pockmarked by the aftereffects of particle impact. Others display oddly uniform star formation rates, as if some unseen hand were smoothing out the bursts and lulls. And then there are the ghost galaxies, faint, diffuse collections of stars that somehow avoided clustering into dense structures. Could cosmic rays have pressurized their gas so thoroughly that gravity never gained a foothold? Yet mysteries linger. If cosmic rays were so influential, why do some early galaxies show runaway starbursts anyway? The answer might lie in the environment. Just as wind shapes sand differently in a desert versus a beach, cosmic rays would have varied in effect depending on a galaxy's location within the cosmic web. Those floating in voids far from supernova-rich filaments might have escaped the particle deluge entirely. Others, caught in dense clusters, could have been bombarded into equilibrium. There's a deeper irony here. The same particles that hindered star formation in one era might have enabled it in another. As cosmic rays ricocheted through space, they could have triggered complex chemical reactions in gas clouds, forming molecules that later cooled into new stars. It's as if the universe devised a self-regulating system, first pressing pause, then play, all with the flick of an invisible particle beam. Astronomers are now racing to test this idea with next-generation telescopes, hunting for the faint gamma-ray glow that would betray ancient cosmic ray activity. If they find it, we might finally understand why galaxies didn't burn too bright or fade too soon, but instead grew at just the right pace to build the universe we know today. Deep in the frigid reaches of the early universe, long before the first stars flickered to life, something bizarre was happening. Hydrogen gas wasn't just floating aimlessly. It was snowing, not the gentle flakes we know on Earth, but vast cosmic snowflakes made of pure hydrogen molecules, drifting through the darkness and clumping together in silent, icy avalanches. This wasn't just a celestial curiosity. It might have been the universe's secret shortcut to building galaxies faster than anyone imagined. Picture a cloud of hydrogen gas so cold, so still, that atoms began pairing up into delicate molecular bonds, like whispers of frost forming on a window pane. In the modern universe, this process is rare. Gas is too warm, too turbulent. But back when the cosmos was just a few 100 million years old, temperatures in certain pockets could have plunged close to absolute zero, colder than the void between galaxies today. In these freezing conditions, hydrogen molecules didn't just drift, they stuck together, growing into intricate fractal flakes light years wide. And just like snow piling up on a mountainside, these flakes collapsed under their own weight, creating dense seeds where gravity could take over. The math behind this is mesmerizing. Simulations show that molecular hydrogen snowflakes wouldn't behave like ordinary gas clouds. Their icy structures would make them far more efficient at shedding heat, allowing them to contract faster and with less resistance. Instead of the slow, grinding collapse of typical nebulae, these snowflakes could have accelerated galaxy formation by millions of years, like cosmic tumbleweeds gathering mass as they rolled through the void. Some models even suggest these icy clumps could have bypassed the need for dark matter halos entirely, forming proto-galaxies from pure hydrogen alone, a heresy by modern astrophysical standards. But here's the twist: not all hydrogen snowflakes were created equal. The shape of these cosmic ice crystals, whether fluffy and porous or dense and compact, could have determined the fate of the galaxies they spawned. Fluffier flakes might have birthed loose, sprawling galaxies with slow-burning stars, while denser clusters could have ignited violent starbursts, lighting up the cosmos like flashbulbs in the dark. Even stranger, some of these snowflakes might have carried microscopic impurities, trace amounts of lithium or helium, acting as catalysts to kickstart chemical reactions we still don't fully understand. The hunt for evidence is like searching for melted snow in a desert. The hydrogen snowflakes themselves vanished billions of years ago, vaporized by the heat of the first stars. But their legacy might linger in the chemistry of the oldest stars. We can observe stars with puzzlingly low amounts of heavy elements, as if they formed from gas that had never been touched by supernova. Other clues could hide in the distribution of dwarf galaxies, which sometimes cluster in ways that defy dark matter predictions, as if they were once anchored to invisible ice patches long since evaporated. Of course, skeptics abound. If hydrogen snowflakes were so efficient, why didn't they overproduce galaxies in the universe's youth? The answer might lie in timing. These icy marvels could only exist in that brief Goldilocks era when the cosmos had cooled enough for molecular hydrogen to form, but before the first stars heated everything up again. A window of opportunity measured in mere millions of years, but one that might have set the stage for everything that followed. There's a poetic symmetry to this idea. Just as snowflakes on Earth require just the right conditions, cold, stillness, a speck of dust to nucleate around, the universe's first galaxies might have needed their own version of a perfect winter night. And if we ever confirm their existence, it would mean the cosmos didn't just build galaxies with brute force and darkness. It crafted them one delicate snowflake at a time. Plasma in the early universe wasn't just hot. It was alive with instabilities so wild they could twist entire regions of space into galaxy-forming whirlpools. Forget the serene images of glowing nebulae we know today. This was plasma with a temper, crackling with electromagnetic tantrums that may have sculpted the first cosmic structures long before gravity got its chance. These weren't your average solar flares, they were titanic plasma vortices, spinning off magnetic knots so powerful they could corral gas into proto-galaxies like cosmic cattle drives. The secret lies in something called the Weibel instability. Picture this: in the seething chaos after the Big Bang, streams of charged particles raced through the plasma at nearly light speed, but not in perfect unison. Tiny misalignments, particles veering slightly left or right, created electromagnetic eddies, like invisible whirlpools in an ocean of fire. These eddies grew rapidly, their magnetic fields intensifying until they began pinching the plasma into dense filaments and knots. Suddenly, what was once a uniform soup became a labyrinth of high-pressure walls and low-density voids, a perfect template for gravity to later amplify into galaxies. Here's where it gets even stranger. These plasma instabilities didn't just create structure, they turbocharged it. Simulations show that under the right conditions, magnetic vortices could funnel gas into dense clumps thousands of times faster than gravity alone. Gas didn't slowly collapse, it was sucked into these swirling electromagnetic traps, like water spiraling down a drain. Some models even suggest that the first spiral galaxies might owe their iconic shapes not to gentle rotation, but to the twisted fingerprints of primordial plasma storms. But the real kicker, these instabilities leave forensic evidence. If plasma vortices really did seed galaxies, we'd expect to find certain magnetic signatures fossilized in the oldest star clusters, subtle alignments of charged particles that trace back to those ancient whirlpools. Astronomers have already spotted tantalizing hints in the polarization patterns of light from distant quasars, their photons twisted by intervening magnetic fields that seem too organized to have formed later. It's as if the universe left us a breadcrumb trail written in magnetism. Of course, not everyone's convinced. Critics argue that plasma instabilities would have been overwhelmed by the universe's expansion, their delicate structures stretched into irrelevance before gravity could take over. Others point out that most modern galaxies show little evidence of these primordial magnetic imprints, their fields seemingly scrambled by billions of years of chaos. Yet proponents counter that we might be looking in the wrong places. Dwarf galaxies, with their simpler histories, could still harbor these magnetic fossils waiting to be decoded. There's a poetic irony here. The same violent plasma that once made the universe uninhabitable might have been the very force that built the homes for future stars and ultimately us. It's a reminder that creation often begins with chaos, and that even the fiercest storms can leave behind the seeds of order. At the smallest scales imaginable, far smaller than atoms, smaller even than protons, space-time might not be the smooth fabric we picture. Instead, it could be a frothing, seething foam, bubbling with virtual particles popping in and out of existence so fast they defy detection. This is the quantum foam, a turbulent sea of spacetime itself, and some theorists propose it didn't just exist passively in the early universe, it might have actively sculpted the first galaxies. Picture this foam not as uniform bubbles, but as a dynamic, churning ocean where some regions randomly grew more energetic than others. In the frenzy of the universe's first moments, these quantum fluctuations could have been stretched to cosmic proportions by inflation, creating microscopic hills and valleys in the very structure of reality. Normally, these wrinkles would be too tiny to matter, but here's the twist. If certain exotic physics are correct, some of these quantum bubbles might have stabilized, anchoring pockets of spacetime where matter could gather more easily. Like cosmic nucleation cites the way a single grain of dust can seed an entire snowflake, these quantum knots could have become the gravitational seeds for galaxies. The math behind this is dizzying. Calculations suggest that in the extreme conditions of the early universe, quantum foam wouldn't just flicker. It could freeze temporarily in dense configurations, creating ultramicroscopic regions of warped spacetime with extra gravitational pull. Over billions of years, these specks would attract matter, growing from quantum quirks into galactic giants. It's as if the universe played a trick on itself. By twisting spacetime at the smallest scales, it laid the foundation for the largest structures we know. Evidence for this idea is predictably elusive, but there are tantalizing hints. The distribution of some ancient galaxy clusters shows odd periodicities spacings that align with predictions from certain quantum foam models. Even stranger, the spins of early galaxies sometimes exhibit unexpected alignments over vast distances, as if they were threaded onto invisible cosmic strings woven by spacetime's primordial froth. Of course, not all physicists are convinced. Critics argue that quantum foam effects would be washed out by the universe's expansion, rendered irrelevant long before galaxies could form. Others propose hybrid models where quantum nucleation worked in tandem with dark matter, each amplifying the other's influence. But if this theory holds, it would mean galaxies aren't just held together by gravity. They're the echoes of spacetime's first quantum whispers written in starlight. What if the missing ingredient in our understanding of galaxy formation wasn't a hidden force or a new particle, but a ghost, interstellar neutrinos, the universe's most elusive phantoms? Unlike their ordinary neutrino cousins, which flit through matter like shadows through a screen, sterile neutrinos would be heavier, slower, and far more reluctant to interact with anything at all. Yet their presence might have warped the behavior of dark matter itself, subtly redirecting the flow of cosmic history into the galaxies we see today. Here's how this ghostly influence could work. In the standard picture, dark matter clumps together under gravity, forming the invisible scaffolding for galaxies. But sterile neutrinos, if they exist, would have added a bizarre twist. Their sheer mass would have generated slight gravitational nudges, while their reluctance to interact would have let them slip through regions of dark matter like a sieve. The result, a cosmic game of gravitational tug-of-war, where dark matter halos didn't just collapse smoothly, but stuttered. Their growth slowed or accelerated depending on the sterile neutrinos' dance. Simulations paint an eerie scene. When sterile neutrinos are added to virtual universes, dark matter doesn't pool as densely in small halos. Instead, it's drawn toward larger structures, as if the invisible threads of gravity were being subtly rewoven. This could solve a long-standing puzzle: why some dwarf galaxies seem to lack the thick dark matter coats predicted by conventional models. If sterile neutrinos smoothed out the smallest clumps, it would mean galaxies didn't just form from the bottom up. They were shaped by an unseen hand, redistributing dark matter like a cosmic croupier shuffling chips across a table. But the plot thickens. Sterile neutrinos wouldn't just tweak dark matter's distribution. They might have left fingerprints in the oldest light we can see. As these particles decayed over eons, they could have injected extra energy into the cosmic microwave background, creating faint temperature ripples that telescopes are only now sensitive enough to detect. Some researchers claim they've spotted hints of these anomalies already, subtle deviations in the microwave sky that align eerily with sterile neutrino predictions. Of course, not everyone's convinced. Critics argue that sterile neutrinos are a solution in search of a problem, an elegant idea, but one that lacks definitive proof. Others point out that alternative theories like warm dark matter can explain the same galactic quirks without invoking such exotic particles, yet the allure remains. If sterile neutrinos are real, they wouldn't just be passive spectators to galaxy formation. They'd be the universe's unseen choreographers, whispering to dark matter in a language we're only beginning to decipher. The hunt for these phantoms is on. Underground detectors, space telescopes, and even neutrino beams are being tuned to catch the slightest trace of their existence. And if they're found, it would mean our cosmic story has been missing a character all along, one that silently shaped the galaxies while hiding in plain sight. After all, sometimes the most powerful forces in the universe aren't the ones that shout, but the ones that never speak at all. What if the universe's first galaxies weren't just three-dimensional objects, but projections of information encoded on a distant, two-dimensional surface? This isn't science fiction, it's the holographic principle, a radical idea from string theory that suggests our entire cosmos, from the smallest atom to the grandest galaxy, might be a hologram. And here's where it gets even wilder. The distribution of those primordial galaxies could be whispering secrets about higher dimensions we can't even perceive. The holographic principle flips everything we think we know about reality. Imagine taking a black hole's event horizon, the point of no return, and realizing all the information about what fell inside isn't lost but smeared across its surface like ink on a balloon. Now scale that up. Some theorists propose the entire universe works the same way, with everything we experience, space, time, even galaxies being a three-dimensional projection of data stored on a two-dimensional boundary at the edge of. Well, everything. It's as if the cosmos were a cosmic DVD, and the galaxies we see are just the movie playing out. But how could this possibly connect to the first galaxies? Here's the twist. If the holographic principle is true, then the patterns we see in galaxy clusters, the way they clump and curve and twist across billions of light years, aren't random. They're a cosmic barcode encoding information from a higher dimensional reality. Think of it like a shadow puppet show. The shapes on the wall seem flat and disconnected, but they're actually being manipulated by hands moving in 3 dimensions. Similarly, the distribution of ancient galaxies might be tracing the fingerprints of physics playing out in dimensions beyond our own. The math behind this is mind-bending. When researchers apply holographic models to the early universe, they find something uncanny. The statistical patterns of galaxy clusters align eerily with predictions for how information will be encoded on a two-dimensional surface. Certain arrangements of galaxies, like the way they cluster at specific angles or distances, match what you'd expect if they were projections of quantum bits or qubits vibrating on a distant cosmic horizon. Even stranger, some simulations suggest that the universe's large-scale structure, the cosmic web of filaments and voids, could be a holographic echo of quantum entanglement in higher dimensions. So where's the evidence? Astronomers might have already found it hidden in the cosmic microwave background. Tiny temperature fluctuations in this afterglow of the Big Bang appear to follow patterns predicted by holographic models, with correlations between distant points that defy classical physics. Some researchers argue this is the universe's way of winking at us, hinting that what we perceive as three-dimensional structure is really just a slice of something far richer. Of course, skeptics abound. If the universe is a hologram, why does it feel so solid? Why can't we detect this elusive two-dimensional boundary? The answers might lie in the nature of spacetime itself. Just as a high-resolution screen can trick the eye into seeing depth, the universe's pixels, Planck-scale units of spacetime, could be so infinitesimally small that their true, flattened nature is hidden in plain sight. Here's the kicker. If the holographic principle shaped the first galaxies, it would mean that every spiral arm, every star, every planet is part of a cosmic illusion, a shadow cast by a reality we're only beginning to decode. And somewhere in the patterns of those ancient galactic clusters, the universe's deepest truth might be written in a language we're just learning to read. Imagine the universe as a vast sheet of frozen ice, stretched impossibly thin, and in that ice, invisible cracks are forming, fractures so perfect they could slice atoms in half. These aren't just flaws in the ice, they're cosmic strings, hypothetical scars in the fabric of space-time itself, and some scientists believe they might have been the universe's first sculptors, carving the earliest galaxies into existence with nothing but the sheer force of their gravitational pull. Here's the mind-bending part: cosmic strings wouldn't behave like anything we know. Thinner than a proton but denser than a mountain range, these one-dimensional defects, left over from the universe's fiery infancy, would carry unimaginable tension, warping space-time around them like a bowling ball resting on a trampoline. As they vibrated and twisted through the cosmos, their gravity wouldn't just tug at nearby matter. It would whip gas into frenzied currents, funneling it into dense ribbons where galaxies could sprout like pearls strung on an invisible wire. Computer simulations reveal something astonishing. When researchers model cosmic strings into virtual universes, galaxies don't form randomly. They align along invisible fault lines, clustering in long, filamentary chains that mirror the string's path. Even more bizarre, the galaxies that form near these strings tend to spin in the same direction, as if some unseen hand had given them all the same twist. It's an eerie echo of what we see in the real universe: galaxies mysteriously aligned over vast distances, their spins synchronized in ways gravity alone can't explain. But cosmic strings wouldn't just guide galaxy formation, they might have turbocharged it. Unlike dark matter, which builds structure slowly through gravity, cosmic strings could have jump-started the process by creating instant density variations in the early universe. Picture dragging a spoon through syrup. The grooves left behind gather more syrup, just as the gravitational wakes of cosmic strings would gather gas. Some theories suggest these strings could have even triggered star formation by sending shockwaves through primordial gas clouds, lighting up the cosmos with starbursts far earlier than expected. Yet the most tantalizing clue might be hiding in the cosmic microwave background. If cosmic strings ever existed, their ultra-dense cores would have bent light in peculiar ways, leaving faint, telltale kinks in the afterglow of the Big Bang. Astronomers have scoured this relic radiation for decades, hunting for these distortions like detectives analyzing a fingerprint. A few anomalous patterns have sparked excitement: straight-line anomalies in the microwave sky that some argue could be cosmic strings' ghostly signatures. Of course, not everyone's convinced. Critics point out that cosmic strings, if they exist at all, would likely be too sparse to explain the universe's full structure. Others argue that alternative theories, like dark matter's gravitational pull, can account for galactic alignments without invoking such exotic physics. But proponents counter that cosmic strings wouldn't replace dark matter. They'd work alongside it, adding fine-grained structure to the cosmic web's broad strokes. There's a haunting beauty to this idea. If cosmic strings are real, the galaxies we see today, including our own Milky Way, might owe their existence to the faintest scars in space-time, relics from a time when the universe was still setting its own rules. And somewhere out there, these ghostly threads might still be vibrating, their whispers echoing through the voids, shaping the cosmos in ways we're only beginning to glimpse. What if everything we think we know about gravity is wrong? Here's a theory that doesn't just tweak the rules, it throws them out entirely. Modified Newtonian dynamics, or MUND, suggests dark matter might be a cosmic mirage. Instead of invisible particles holding galaxies together, gravity itself could behave differently on vast scales, bending reality in ways Newton and Einstein never saw coming. At the heart of MUND is a simple but radical idea. Gravity doesn't weaken as quickly over distance as we've assumed. On Earth and in our solar system, Newton's laws hold up beautifully. Planets orbit predictably, apples fall straight down. But venture into the emptiness between stars and something peculiar happens. The outer edges of galaxies rotate far faster than they should, as if gripped by some unseen hand. Dark matter has been the go-to explanation for decades, but MND offers a daring alternative. What if gravity at these extreme scales doesn't follow the inverse square law? What if it plateaus, creating a hidden force that keeps stars from flying off into the void? The math behind this is deceptively elegant. MND introduces a tiny but critical tweak, a minimum acceleration threshold below which gravity's behavior shifts subtly. Below this threshold, about 1/10 billionth of the gravity we feel on Earth, the equations change. Suddenly, the rotation curves of galaxies snap into place without invoking dark matter at all. It's like discovering a hidden gear in a clockwork universe, one that's been quietly ticking away unnoticed. Supporters of MND point to eerie consistencies. Certain dwarf galaxies, for instance, move in ways that dark matter struggles to explain but align perfectly with MND predictions. Even more compelling, some galactic collisions, like the famous bullet cluster, show gravitational effects that don't neatly map onto dark matter's expected distribution, yet MND accounts for them naturally. It's as if the universe left us breadcrumbs and they trace a path straight to rewritten laws of physics. But here's where things get thorny. If MND is correct, why doesn't it explain everything? Galaxy clusters, for example, still seem to need extra mass to hold together unless you fine-tune the theory further. And then there's the cosmic microwave background, whose patterns fit snugly with dark matter models but require gymnastic adjustments under MND. Skeptics argue this isn't a cleaner solution, just a different kind of complexity. Yet the allure remains. MND forces us to confront an unsettling possibility. Maybe we've been inventing invisible matter to patch over gaps in our understanding, when the real fix lies in reimagining gravity itself. It's a cosmic Copernican moment. What if the flaw isn't in the stars but in our equations? The debate rages on, but one thing's certain. Whether MND ultimately triumphs or falls, it's shattered the illusion that we've got gravity all figured out. Sometimes the most revolutionary ideas aren't about adding pieces to the puzzle, they're about realizing we've been holding the pieces wrong the whole time. Black holes aren't just cosmic vacuum cleaners, they're also cosmic radiators. According to Stephen Hawking's revolutionary theory, even these gravitational monsters can't hold onto energy forever. They slowly leak it back into the universe through what we call Hawking radiation, a faint whisper of particles escaping their event horizons. Now imagine this process not in the supermassive black holes of today, but in tiny, primordial ones, black holes no heavier than a mountain, forged in the chaos of the Big Bang itself. These pint-sized beasts wouldn't live for billions of years like their modern cousins. They'd evaporate in bursts of energy so intense, they might have cooked the early universe's gas in ways we're only beginning to understand. Here's the twist: Hawking radiation isn't just heat, it's a particle factory. As a tiny black hole evaporates, it spews out everything from photons to electrons, even exotic heavy particles, if theories about high-energy physics hold true. In the dense, pristine gas of the early cosmos, this radiation could have acted like a cosmic chemist, ionizing hydrogen, smashing atoms apart, or even catalyzing the formation of complex molecules long before stars had a chance to. Picture the universe's first gas clouds not as quiet nurseries, but as seething labs bombarded by particle beams from dying black holes, their chemistry rewritten with every burst. The numbers are staggering. If enough of these micro-black holes existed, their combined evaporation could have heated vast regions of space, delaying star formation in some areas while supercharging it in others. Some simulations suggest these bursts might have created bizarre, temporary elements, short-lived isotopes that don't exist in nature today, but could have left ghostly traces in the spectra of the oldest stars we can observe. It's as if the universe had its own built-in particle accelerators, flickering on and off like cosmic strobe lights, each one tweaking the recipe for galaxy formation in real time. But the weirdest implication, Hawking radiation might have been a double-edged sword. While it enriched some regions, it could have sterilized others. Too much radiation near a budding protogalaxy could have stripped away its gas, leaving it stunted and starved. That might explain why some corners of the early universe seem oddly empty, their potential galaxies zapped into oblivion by evaporating black holes they never even saw coming. Of course, not everyone's convinced. If these primordial black holes were so influential, where's the evidence? Some researchers argue we've already found anomalous heat signatures in the cosmic microwave background, or mysterious X-ray sources with no clear origin. Others are hunting for the gravitational echoes of black hole deaths, subtle ripples in spacetime that might still ripple through the cosmos today. One thing's certain: if Hawking radiation really did tinker with the early universe's chemistry, it would mean black holes weren't just destroyers, they were alchemists shaping the cosmos not just with gravity but with their dying breath. And somewhere in the faint glow of those ancient gas clouds, their fingerprints might still be waiting. Neutrinos are the universe's most elusive particles, ghostly, nearly massless, and capable of passing through light years of lead without a single collision. But what if these cosmic phantoms weren't just passive spectators in the early universe? What if they were actively wrestling with dark matter itself, tangling in an invisible dance that delayed the birth of galaxies? That's the startling premise of neutrino dark matter scattering, a theory suggesting the universe's most abundant yet mysterious particles might have been locked in a gravitational tug-of-war that shaped everything we see today. Here's how it could have happened. In the early universe, neutrinos weren't the solitary drifters we know now. They were a seething, high-energy swarm, ricocheting through space at nearly the speed of light. Meanwhile, dark matter, the universe's invisible scaffolding, was busy clumping into the halos that would later anchor galaxies. Normally, these two wouldn't interact at all. But if a fraction of dark matter particles carried even a whisper of electric charge or interacted via some undiscovered force, everything changes. Neutrinos, usually indifferent to matter, could have slammed into dark matter like bullets hitting smoke, transferring just enough energy to slow dark matter's collapse. The effect would be subtle but profound. Think of it like trying to build a sandcastle in a stiff breeze. Without wind, the sand piles easily. But with gusts scattering grains, the structure takes longer to form. In the cosmic context, neutrino dark matter scattering might have acted like that wind, gentle enough not to stop galaxy formation entirely, but strong enough to stretch the timeline. Supercomputer simulations reveal something mesmerizing. When you introduce even weak interactions between neutrinos and dark matter, the first galaxies flicker to life noticeably later than in conventional models. Some regions might have lagged by hundreds of millions of years, as if the universe itself hit a cosmic pause button. But here's the twist: this delayed start could solve one of astronomy's lingering puzzles: why some of the earliest galaxies we've spotted seem just a little too mature for their age. If neutrino dark matter scattering slowed initial structure growth, it would mean the galaxies we observe in the universe's adolescence had extra time to evolve behind the scenes before their light reached us. It's like finding a toddler who can already solve calculus unless, of course, they've secretly been around longer than we thought. The hunt for evidence is already underway. Astrophysicists are scouring the cosmic microwave background for telltale distortions, patterns in the universe's oldest light that could betray early neutrino dark matter tussles. Others are comparing galaxy distributions across cosmic time, searching for statistical anomalies that align with this breaking effect. Even terrestrial neutrino detectors like Japan's Super Kamiokande might hold clues as they refine their ability to measure neutrino properties with impossible precision. Yet mysteries remain. If neutrinos and dark matter interacted, why don't we see more dramatic disruptions in modern galaxies? The answer might lie in the cooling of the universe. As space expanded and temperatures plummeted, neutrinos lost energy, becoming the aloof wanderers we know today, too slow and sparse to keep tangling with dark matter. Their golden age of influence was fleeting, a brief but pivotal chapter written in the universe's opening pages. There's a poetic symmetry to this idea. The same particles that now slip through our detectors like whispers might once have shaped the cosmos with the force of a shout. And if this theory holds, it means galaxies weren't just built by gravity and darkness. They were forged in the quiet conflict between two phantoms, each as mysterious as the other. Suppose the universe's first galaxies weren't built by the particles we know, but by ones we've never seen. Enter supersymmetry or SUSY, a theory so elegant it promises to solve half of physics' greatest puzzles at once. At its heart is a dazzling idea. For every known particle in the cosmos, electrons, quarks, photons, there exists a hidden twin, a superpartner with bizarre properties that could have secretly orchestrated the birth of galaxies. These aren't just abstract hypotheses. SUSY particles or sparticles would carry game-changing traits. Take the neutralino, a hypothetical mashup of supersymmetric particles that doesn't just interact with gravity like dark matter, but annihilates itself in bursts of energy. In the early universe, that self-destruction could have been the spark that lit the fuse of galaxy formation. Picture this: as neutralinos collided and vaporized, their death throes would have flooded space with radiation and subatomic shrapnel, heating some regions of gas while compressing others. These violent pockets might have become the gravitational seeds for the first protogalaxies, their growth supercharged by the very particles that vanished to create them. Here's where it gets wild. Unlike traditional dark matter, which clumps passively under gravity, supersymmetric dark matter could have actively sculpted the cosmos. Some sparticles might have carried faint electromagnetic charges, allowing them to nudge ordinary matter like cosmic billiard balls. Others could have decayed into exotic particles that altered the chemical balance of primordial gas, making it cool faster or slower in key regions. Computer simulations reveal something mesmerizing. When you plug SUSY particles into models of the early universe, galaxies don't just form. They crystallize, their distribution matching observed patterns better than standard dark matter alone. Yet the most tantalizing clue lies in the cosmic microwave background. SUSY predicts subtle ripples in this afterglow, patterns of temperature variation that align eerily with observations from Planck satellite data. It's as if the universe left us a breadcrumb trail, and it leads straight to supersymmetry's doorstep. Even more compelling, certain ancient star clusters show chemical abundances that defy conventional astrophysics unless you factor in sparticle-driven reactions that could have occurred nowhere else. Of course, not everyone's convinced. Despite decades of searching, particle colliders like the LHC haven't spotted sparticles directly, leaving some physicists skeptical. Others argue that while SUSY elegantly explains galaxy formation, it might be overkill, like using a quantum supercomputer to balance a checkbook. But proponents counter that we've only scratched the surface. If sparticles are heavier than expected or conceal themselves in extra dimensions, our detectors might need revolutionary upgrades to catch them in the act. There's a poetic irony here. The particles we've never seen might have built the galaxies we know best, and if SUSY is real, it would mean the cosmos isn't just stranger than we imagined. It's more symmetrical, hiding mirrors within mirrors at every scale. The hunt for these shadow particles continues not just in atom smashers, but in the very structure of the night sky where ancient starlight might still carry their fingerprints. Energy isn't just something stars produce. It might have once flooded the entire cosmos like an invisible tide, holding back the birth of galaxies themselves. Picture the early universe not as a quiet cradle for structure, but as a battleground where repulsive phantom energy fields, forces far stranger than dark energy, fought gravity's pull, pressing pause on galaxy formation for hundreds of millions of years. These weren't gentle ripples in spacetime. They were cosmic overrides saturating the universe with enough anti-gravitational push to keep gas clouds from collapsing, as if the cosmos had hit a giant snooze button on its own evolution. The mechanics of this are mind-bending. Unlike dark energy, which works at vast scales to accelerate the universe's expansion today, phantom energy in the early universe could have been stronger, more concentrated, even temporary. Some theories suggest it emerged from the same quantum foam that birthed spacetime itself, a leftover surge from the Big Bang that hadn't yet dissipated. Its repulsive force would have acted like an invisible shield around pristine gas clouds, counteracting gravity's pull just enough to keep matter suspended in a kind of cosmic limbo. Supercomputer simulations show the eerie result. When phantom energy dominates, proto-galaxies don't just form slowly. They stall entirely, their gas hovering in diffuse, frustrated clouds until the field's influence finally fades. But here's where the plot twists. Phantom energy's temporary nature might explain one of cosmology's biggest puzzles: why galaxies seem to appear in the cosmic record slightly later than some models predict. If these fields were active during the universe's first few 100 million years, they could have imposed a universal delay, like a regulatory hand ensuring galaxies didn't ignite too soon. Then, as phantom energy decayed, perhaps transferring its energy into spacetime itself, gravity finally gained the upper hand, triggering synchronized bursts of star formation across the cosmos. It's as if the universe had a built-in timer, a fleeting epoch where creation was put on hold until conditions were just right. Evidence for this might already be hiding in plain sight. Astronomers have noticed odd gaps in the timeline of early galaxy formation periods where star birth seems suspiciously subdued, followed by sudden surges. Some distant gas clouds also show peculiar chemical signatures, as if they'd been stirred but not shaken by an unseen force. Even the cosmic microwave background bears faint asymmetric patterns that could be scars from phantom energy's reign, like tide marks left by a receding wave. Of course, skeptics pounce on the unknowns. If phantom energy was so powerful, why didn't it prevent structure formation entirely? The answer might lie in its interaction with dark matter. Some models suggest dark matter's gravity could have created localized pockets where phantom energy's influence was weaker, allowing a handful of galaxies to form early as cosmic outliers. These rare overachievers galaxies that shouldn't exist under the prevailing conditions might now be the key to spotting phantom energy's fingerprints. The implications are staggering. If phantom energy fields really did delay galaxy formation, it would mean the cosmos wasn't just shaped by gravity and matter, but by ephemeral forces that came and went like cosmic mood swings. The galaxies we see today might owe their existence to an ancient energy that vanished without a trace, leaving behind only the faintest echoes in the arrangement of stars. And if we learn to read those echoes, we might uncover something even more profound: that the universe doesn't just build, it waits. Now imagine an ocean of particles so cold, so still, that they stop behaving like individuals and merge into a single quantum entity, a Bose-Einstein condensate. But not in some lab on Earth, across the entire early universe. This is the bizarre realm of action condensates, where hypothetical particles lighter than a whisper could have clumped into galaxies, shaping quantum waves on a cosmic scale. Actions aren't your average dark matter candidates. Born from theories trying to solve one of particle physics' deepest puzzles, why the strong nuclear force obeys perfect symmetry, these ghostly particles would be billions of times lighter than electrons, barely interacting with light or matter. But here's the twist. In the cold, dense aftermath of the Big Bang, their quantum weirdness might have kicked into overdrive. As the universe expanded and cooled, actions could have undergone a phase transition more dramatic than water, freezing into ice, condensing into a single, coherent quantum state stretching across light years. Picture the entire cosmos threaded with invisible superfluid rivers, their flow dictated not by gravity alone, but by the rules of quantum mechanics playing out at macroscopic scales. These condensates wouldn't just sit there. Quantum mechanics grants them bizarre properties like zero viscosity or friction. Action rivers could have sliced through ordinary matter like lasers through mist, carving precise channels where gas accumulated into proto-galactic clumps. Some simulations show these quantum flows organizing dark matter into intricate lace-like patterns, filaments, and voids matching the cosmic web we observe today. Even stranger, because Bose-Einstein condensates are fundamentally wave-like, action dark matter wouldn't clump into neat spheres like traditional models predict. Instead, it would form interference patterns, with galaxies blooming at the peaks of these quantum ripples like flowers in a fractal garden. The fingerprints of this process might still be visible. Action condensates would leave subtle signatures in the rotation curves of modern galaxies, their outer stars orbiting slightly differently than standard dark matter predicts. Some astronomers argue we've already spotted these anomalies in ultra-diffuse galaxies, where gravity seems to ripple in ways that defy conventional physics. Even more tantalizing, certain quasars flicker with periodic brightness variations that align eerily with predictions for action waves passing through their accretion disks. Yet the wildest implication isn't just how actions shaped galaxies, it's what they're doing now. If these condensates persist, the universe today might be crisscrossed by quantum interference patterns we're only beginning to detect. Every galaxy, every star could be bobbing in an invisible quantum sea we've yet to learn how to see. What if the first galaxies weren't faint because they were small, but because their gravity was literally slipping away into other dimensions? This isn't just wild speculation. It's a radical idea rooted in string theory, where our universe might be a three-dimensional island floating in a higher dimensional sea. And if gravity, unlike other forces, can leak into these extra dimensions, it could rewrite everything we thought we knew about how the earliest galaxies took shape. Picture gravity as a force that doesn't just bend space-time, it bleeds through it. In the everyday world, this effect would be negligible, like water slowly seeping through a sieve. But in the sparse, vast stretches of the early universe, where matter was thinly spread and gravitational fields were weak, that leakage could have been catastrophic. Proto-galaxies struggling to pull themselves together might have lost a fraction of their gravitational grip to unseen dimensions, leaving their gas clouds too loose to collapse efficiently. The result, galaxies that flickered where they should have blazed, their starlight dimmed not by lack of material, but by a fundamental flaw in how gravity operated at cosmic scales. The math behind this is dizzying. In some higher dimensional models, gravity's strength follows an inverse cube law instead of inverse square, meaning it weakens far faster over distance. Run the equations backward and you find something startling. Early galaxies in such a universe would need up to 10 times more mass to achieve the same luminosity we observe today. That discrepancy aligns eerily with observations from the James Webb Space Telescope, which has spotted ancient galaxies that seem suspiciously feeble for their size. It's as if we're seeing shadows of galaxies. Their true gravitational might diluted by dimensions we can't perceive, but here's where it gets stranger. Extra-dimensional leakage wouldn't just weaken gravity, it could have distorted its effects in bizarre ways. Some theorists suggest that if higher dimensions were warped or compactified at microscopic scales, gravity might have behaved differently depending on direction. A protogalaxy forming near a hidden dimensional fold could have ended up lopsided, with stars clustering unevenly along the axis of leakage. We might already have evidence of this. Certain ultra-distant galaxies show puzzling asymmetries, their stars arranged in spirals or arcs that defy conventional formation models. The hunt for proof is as creative as the theory itself. Physicists are scouring neutron-star collisions for gravitational waves that might carry hidden imprints of extra dimensions, subtle vibrations in spacetime that don't match four-dimensional predictions. Others are modeling the cosmic microwave background for telltale patterns that could reveal gravity's missing energy. Even particle colliders are in on the act, searching for exotic particles like gravitons that might briefly tunnel into higher dimensions before decaying. Of course, skeptics pounce on the biggest hurdle. If gravity leaks, why don't we see the effects everywhere? The answer might lie in cosmic evolution. As the universe expanded and matter clumped into denser structures, the gravitational fields around galaxies grew strong enough to resist leakage, like a thickening membrane sealing its own cracks. What we're seeing in the earliest galaxies could be a snapshot of a fleeting era, a time when the rules of gravity weren't set in stone and other dimensions still tugged at the fabric of reality. There's a haunting beauty to this idea. The faintest galaxies in our telescopes might not be cosmic afterthoughts, but messengers from a stranger, richer universe, one where gravity hasn't just shaped the heavens but slipped between them. And if they're right, the dimensions we call home could be just the first layer of a reality far deeper than we ever imagined. What if the laws of physics weren't always set in stone? There's a theory that flips everything we know about constants upside down, suggesting gravity, electromagnetism, and even the speed of light might have been different in the early universe. Imagine a cosmos where the fundamental forces weren't just stronger, they were turbocharged, hurling galaxies together with a ferocity that defies modern physics. This isn't science fiction, it's the mind-bending premise of time-varying constants. And if true, it could explain why ancient galaxies look suspiciously mature for their age. Think of the universe's constants like dials on a cosmic control panel. Today, they're locked in place. Gravity's pull is measured to 1 part in 100 trillion, and light speed is unwavering. But rewind 13 billion years, and those dials might have been turned up. Some theories propose that gravity, in particular, could have been significantly stronger in the universe's infancy. With just a few % more gravitational oomph, gas clouds wouldn't have needed dark matter's help to collapse. They'd have imploded into galaxies in a fraction of the time. Recent observations of surprisingly massive galaxies in the early universe, like the colossal Sparkler galaxy spotted by the James Webb Telescope, suddenly make sense if the rules were temporarily rewritten. The math behind this is dizzying. If the fine structure constant which governs electromagnetism was slightly larger in the past, stars would have burned hotter and faster, spewing out heavy elements at breakneck speed. This could explain why some of the oldest stars we've found are polluted with metals, as if they'd formed from gas already enriched by generations of supernova. Even light speed isn't sacred in these models. If photons traveled faster long ago, it would resolve the horizon problem, the eerie uniformity of the cosmic microwave background, without needing inflation. It's as if the universe had a brief era of physics on steroids, then settled into the calm we observe today. But how do we test such a radical idea? The answers might be written in starlight. Quasars, those brilliant beacons from the early universe, shine through ancient gas clouds, leaving absorption lines in their spectra like barcodes. By comparing these lines to lab measurements, astronomers hunt for tiny shifts that could betray changing constants. So far, the evidence is tantalizing but inconclusive. Some studies claim to see variations in the fine structure constant at cosmic distances, while others find nothing. Even more compelling are the nuclear reactors hidden in Africa's Oklo uranium deposits. These natural fission sites, active 2 billion years ago, left behind isotopic ratios that act as frozen snapshots of physics past. Their data suggests the strength of the nuclear force hasn't budged, but gravity's history remains an open question. Of course, skeptics aren't convinced. If constants varied, why don't we see wild inconsistencies in modern experiments? The answer might lie in phase transitions, brief epochs where the universe's underlying vacuum state shifted, locking constants into today's values like ice crystallizing from water. Until we uncover definitive proof, time-varying constants remain a thrilling, what if one that dares us to question whether the universe ever played by the same rules twice. At the farthest edges of our cosmic imagination lies one of the most radical ideas in physics. What if the Big Bang wasn't the beginning, but the echo of something even more extraordinary? Enter white holes, the hypothetical twins of black holes, spewing matter and energy outward instead of sucking it in. Unlike their dark counterparts, white holes are purely theoretical mathematical solutions to Einstein's equations that most physicists dismiss as impossible. But what if these cosmic fountains weren't just scribbles on a chalkboard? What if their remnants lingered after the Big Bang, imprinting themselves onto the newborn universe in ways we're only beginning to uncover? Here's the wild connection. Some theorists propose that clusters of ultra-dense white hole remnants could have seeded regions of intense galaxy formation in the early cosmos. Imagine these relics not as singular points, but as gravitational beacons, regions where space-time itself was still ringing from the violence of their creation. As the universe expanded, these zones would have acted like cosmic breadcrumbs, pulling in matter with gravitational fingerprints unlike anything produced by ordinary dark matter. The result, hyperactive pockets of star birth where galaxies didn't just form. They erupted, packing thousands of stars into volumes of space that should have taken billions of years to fill. We might already be seeing hints of this. Some of the densest galaxy clusters in the early universe, like the Pandora cluster or the proto-cluster SPT 234956, defy conventional formation timelines. These ancient metropolises of light host hundreds of galaxies crammed into an area just a few million light-years across, as if something had jump-started their growth long before physics should have allowed. Intriguingly, their distribution isn't random. They align along vast, invisible arcs that eerily resemble predictions for how white hole debris might scatter after a Big Bounce event. A hypothetical cycle where a collapsing universe rebounds into a new Big Bang. But how would these remnants even survive? White holes, by definition, are unstable mathematical unicorns that should instantly collapse into black holes under any real-world conditions. That's where quantum gravity steps in. Some models suggest that in the Planck epoch, the universe's first incomprehensibly tiny fraction of a second quantum effects could have stabilized microscopic white hole kernels. These wouldn't be the planet-swallowing monsters of sci-fi, but ultra-dense specks of warped spacetime, each no larger than a proton yet massive enough to warp their surroundings for eons. As the cosmos expanded, they'd have decayed, their energy bleeding into the fabric of space itself, but not before leaving behind gravitational scars where matter would later pool. The smoking gun might lie in gravity waves. If white hole remnants really did shape early galaxies, mergers between their descendants could have produced high-frequency gravitational ripples unlike anything from black hole collisions. Next-generation detectors like the Einstein telescope might soon catch these whispers from the dawn of time. Until then, the theory remains a beautiful enigma, one that dares us to rewrite not just how galaxies formed, but where the universe itself came from. After all, if white holes seeded the cosmos, then every star we see might just be the afterglow of a reality that came before. Imagine a universe where gravity wasn't the only force binding galaxies together, where particles separated by vast cosmic distances could whisper to each other instantly, linking the fate of stars and galaxies in an invisible quantum web. This is the wild frontier of entanglement gravity, a theory proposing that quantum entanglement, the same spooky connection Einstein famously doubted, could have played a hidden role in sculpting the universe's first structures. At the quantum level, entanglement is downright bizarre. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. In labs today, we've seen this phenomenon span hundreds of kilometers, defying classical notions of space and time. But in the early universe, conditions were so extreme that entanglement might not have been limited to tiny particles. It could have scaled up to cosmic proportions. Picture the primordial plasma, a seething ocean of particles so dense that entanglement could have spread like wildfire, creating a network of instant connections across the entire cosmos. Here's where gravity enters the picture. Normally, gravity acts locally. Planets pull on nearby moons, stars tug at orbiting planets. But if entanglement linked widely separated clumps of matter, it could have created a kind of non-local gravitational effect. Regions of space that should have been too far apart to influence each other might have acted in eerie unison, collapsing into galaxies faster than gravity alone could explain. Some models suggest this could resolve a persistent puzzle: why certain galaxy clusters appear more synchronized than standard cosmology predicts, as if they'd been in silent conversation since the dawn of time. The mechanics are mind-bending. In conventional physics, gravity propagates at the speed of light, sluggishly building cosmic structures over eons. But entangled particles don't care about distance. Their connection is instantaneous. If entangled matter carried even a fraction of gravitational influence, it could have acted like a cosmic shortcut, allowing proto-galaxies to feel each other's presence across the infant universe. Supercomputer simulations hint at something astonishing. When entanglement is factored into early universe models, galaxies form in tighter, more intricate clusters than gravity alone would produce, mirroring the intricate webs we observe in deep-field telescope images. Yet entanglement gravity isn't without its skeptics. If this effect were so powerful, why don't we see blatant violations of locality in modern galaxies? The answer might lie in decoherence, the process by which quantum systems lose their delicate entangled states. As the universe expanded and cooled, interactions with radiation and matter would have shattered these fragile connections, leaving only gravity's slower, familiar hand to shape later structures. The imprint of entanglement gravity, if real, would be fossilized in the earliest galactic arrangements, subtle patterns we're only now learning to decode. The hunt for evidence is already underway. Astronomers are scouring quasar light for anomalies in polarization, tiny twists that could betray ancient entanglement networks. Others are analyzing the cosmic microwave background for statistical fingerprints of non-local quantum links. Even gravitational wave detectors might one day catch whispers of entanglement's role, if mergers between primordial black holes carry echoes of their quantum past. There's a poetic symmetry to this idea. The same quantum magic that powers modern technologies like quantum computers might have once woven the fabric of the cosmos itself. And if entanglement gravity holds up, it would mean the universe's first galaxies weren't just pulled together. They were stitched into existence by threads of quantum connection we're only beginning to unravel. What if the bizarre quirks of the earliest galaxies aren't cosmic accidents but digital artifacts from a universe-sized simulation? Picture this: our reality isn't the base layer of existence, but an advanced computational construct, and those inexplicably mature galaxies. They're rendering errors in the code. This isn't just sci-fi speculation, it's a provocative lens through which some theorists reinterpret the universe's glitches. Take the impossible galaxies spotted by the James Webb Space Telescope, colossal structures that seem too massive, too evolved for their age. In simulation theory, these could be buffer overflows, regions where the simulation's memory allocation faltered, cramming in more stars than the physics engine should allow. Like a video game struggling to render distant terrain, the early universe's draw distance might have cut corners, stitching together patchy approximations that later telescopes reveal as anomalies. Even the oddly synchronized spins of ancient galaxies could hint at optimization shortcuts, a developer recycling rotational values to save processing power. But the most tantalizing artifacts might lurk in the cosmic microwave background. Just as compressed JPEG leave telltale pixelation, a simulated universe could bear digital fingerprints in its oldest light. Some researchers point to bizarre concentric circles in the CMB patterns with no natural astrophysical explanation. as potential evidence of recursive code or even save points in the simulation's timeline. Others analyze quantum indeterminacy, suggesting the universe's fuzzy uncertainty at small scales isn't fundamental, but a deliberate, lossy compression to reduce computational load. Of course, skeptics counter that invoking simulation is a cosmic cop-out, an unfalsifiable shrug where science should seek answers. But proponents argue it's no weirder than multiverses or extra dimensions, just another framework to probe reality's seams. After all, if we're living in someone's physics engine, those early galaxies might not be bugs at all. They could be deliberate Easter eggs, clues left by programmers to see if we'd ever think to look. From black holes birthing galaxies to quantum foam imprinting cosmic blueprints, we've journeyed through 30 mind-bending theories about the universe's first galaxies, each one stranger than fiction. Some suggest primordial stars the size of solar systems lit the fuse, while others argue galaxies crystallized from invisible dark matter scaffolds or even emerged from the death throes of white holes in a previous cosmos. The wildest ideas propose holographic projections, entangled quantum destinies, or phantom energy fields pressing cosmic pause on creation itself. Now, thanks to the James Webb Space Telescope, we're closer than ever to separating cosmic fact from speculative fantasy. Every deep field image JWST captures is a time machine to the universe's infancy, and already its findings are turning heads, those shockingly massive galaxies spotted in the early cosmos. They're either upending conventional timelines or hinting at exotic physics like stronger gravity or phantom energies fade out. The eerie alignments of ancient galactic spins could validate cosmic strings' gravitational choreography or point to quantum entanglements' forgotten role. Even the telescope's puzzling empty voids might trace back to primordial black hole evaporation or sterile neutrino interference. With each new observation, the universe isn't just answering our questions, it's daring us to ask better ones. But here's the real magic. You're witnessing this revolution in real time. The data pouring in now could rewrite textbooks within years, not decades. Maybe JWST will find population 3 stars chemical fingerprints, catch a direct collapse galaxy mid-formation, or spot a dark matter filament glowing with action decay. Or perhaps it'll uncover something no theorist predicted, because history shows the cosmos loves a good plot twist. So which theory resonates with you? Are you team cosmic strings, convinced spacetime's ancient scars strung the first galaxies into existence? Or do you bet on holographic entanglement, where the universe's code glitches into grandeur? Drop your favorite in the comments, because the most thrilling part of science isn't having all the answers. It's the collective gasp when we realize the universe is stranger, wilder, and more wondrous than we ever dreamed. And whatever JWST reveals next, one thing's certain: the story of the first galaxies is still being written, and we all get a front row seat.